First of all, let's take a look at metamorphism. If we just look at the basics, there's two big ways that metamorphism happens. One is called contact and the other is called regional. Contact is when there's an igneous intrusion, and if you are a rock right next to an intrusion, can you imagine that? Heat, under pressure, maybe some chemically active fluids coming by. That's going to change the rock, and that will make it metamorphic, but only in that zone. So if you go out from a couple of inches to tens of feet, you're going to transition back to the original rock. The other type is regional. So if you look at what happens with plate tectonics, with these tectonic plates coming along and sometimes colliding, they're going to make big mountains. And when they make mountains, that's going to be collisional stresses. And it covers a very large area, and that's why we call it regional metamorphism. Most of New England is regionally metamorphic, and it's illustrated by the map that you see here. You can see that there are broad stripes here. There's a pattern to this metamorphism, and now I'm going to tell you why these stripes are pretty much aligned north-south. When continents collide, they're going to squeeze an ocean that's in between them. You know, between every continent, there's an ocean. How about that for a concept? That ocean has loads of sedimentary layers. So when you have a collision of continents, those sedimentary layers are going to squeeze up in a certain way. The direction of the folding that's going to happen, folding, and when the rocks break, it's called faulting. So the direction of the folding and the faulting will be perpendicular to the stress. Here's a piece of paper, and notice that when my hands come together this way, the folding goes perpendicular to the stress. So the stress is left to right, and the folding is going to be perpendicular to that. And so if you think of continents coming together, they squeeze the layers and metamorphose them in north-south directions, because they were coming from east and west. Here's our piece of paper illustration. It's going to come together all sorts of squeezing. And notice how all the complicated folding here is perpendicular to the direction of stresses. Now this is an experiment that you can do at home. One thing about metamorphic rocks is each metamorphic rock came from a protolith. That means a beginning rock. And so it's always important when you're looking at metamorphic rocks to understand the protolith origins of those rocks. If we take a look at the sediment, mud becomes shale. But if you put shale under pressure, what happens is something really interesting, and certainly read your book and see Katrin Weiss's video on this to explain it more fully. But when you take mud under pressure, it transitions to slate. Now slate breaks, and you've all seen slate roofs and how slate breaks along very definite planes, but those are not the bedding planes. And that's what's so interesting about slate. And the shale layers get metamorphosed perhaps by some lateral squeezing. There's mica that starts to grow. And when that mica starts to grow, you all know what mica looks like. It's very flat. So when these tiny bits of mica start to grow, the little flakes of mica start to grow perpendicular to the pressure. And so the breakage of the slate, when this shale becomes slate, the breakage along the slate layers is along those mica flakes. So it's breaking at a different angle and direction from the original bedding. Isn't that intriguing? Now let's take slate and metamorphose that to a higher level, because there's various grades of metamorphism. You can have lower grades under lower temperatures and pressures, and you can have higher grades of metamorphism. If we take the slate and we metamorphose it to a higher metamorphic grade, the mica flakes grow and grow and grow. They grow even bigger, and this gives us the rock known as schist. And when you go to your Washington School collection, you can see these. You can see how the schist is more shiny, and you can see the slate has a bit of a sheen to it. The mica flakes are really tiny. If we take a granite with its random texture, right? Granite has a randomness to it like all igneous rocks. And if we put this under heat and pressure, guess what? Those minerals are going to start to recrystallize and move. And they become a very common metamorphic rock that we call gneiss. So look at the banding in this rock. This rock used to be a granite with random light and dark minerals, but like I said, under heat and pressure, they start to move and recrystallize and become a banded rock gneiss. The sand grains are enlarged and they've all grown together. They've recrystallized to become pieces that are kind of grainy, but they're all just merged together. And you can actually kind of see some of the old sedimentary layering preserved in this metamorphic rock. So this is a quartzite. Another great protolith to metamorphic rock combination is what happens to limestone. Limestone is a very common sedimentary rock, although we do not find it in the Connecticut Valley to any great extent at all. But if you're near old ocean deposits, you find loads of limestones. So if you take limestone and metamorphose it, the calcite components of limestone will get larger and larger and larger and become marble. You have a very nice example of marble here, number 38 in your Washington collection. And when you rotate it in the light, you can see that there's lots of sparkly shines here. And those are the calcites. And I'm sure you remember that calcite has 3 planes of cleavage. When you break marble, there's loads of those flat cleavage planes that you see reflecting back at you. Now, marble can often be confused with quartzite, number 40. So they're both light colored and they look very, very, very similar. So how are you going to tell one from the other? Well, marble is made up of calcite, but the quartzite is no surprise, made up of quartz. And if you remember your mineral characteristics, calcite has a hardness of quartz has a hardness of glass has a hardness of about. It's midway in the Mohs hardness scale. So calcites are softer than glass and quartz is harder than glass. And so you'll find that any geology field camp will have lots of beer in bottles. Yes, because bottles will give you glass to do the hardness test. Marble will just skate right over the surface. Here's your quartzite. There's the scratch. You can just feel it right there. Well, this completes our quick look at metamorphic rocks. Next, I would like to take you through how to identify rocks in general. So, first of all, remember that all rocks are categorized based on their texture and then, of course, their composition. But texture is the most important one because the texture tells you about the origin. And as I've often said, it's the texture that tells the tale, tells you the story. So, when you find a rock that you must identify, the first thing you have to do is look at the texture and try to figure out if it's an igneous, metamorphic, or sedimentary texture. So what do you look for? If you have an igneous rock, you have a random texture. If it's coarse-grained, of course, you can see the crystals within it and you know that it was a slow-cooled igneous rock. And if it is fine-grained, like this piece of basalt here, you can't see the minerals within it, but there's no other structures here. It's just an ugly dark rock. That's what we have here, typical basalt characteristic. If it's a metamorphic rock, you will find some kind of weird things here. Let's let's take this this gneiss here, for instance. You can see that it has these layers, and one of the mistakes that beginning students make is they see a rock that's layered and they automatically think sedimentary. But this is not sedimentary layering. The layering that you see here are all due to intergrown crystals. There are not pieces of sand and gravel here at all. You know, it's all intergrown crystalline structure here. So that's the characteristics of a metamorphic rock. This piece of gneiss has a fault in it. Look at that. The layers don't exactly line up. And so sometime after this rock was formed, after it became metamorphic, and then erosion was taking place to get this rock towards the surface of the earth where it would become cooler, it was affected by an earthquake. And the earthquake cracked the rock, and this is the little mini fault right here. The earthquake moved, the rock cracked, and there it is. If this was happening during the time of metamorphism, the rock would have been too malleable, too hot and squishy to actually break and move. It would have folded. So the fact that it's broken tells me that this had to happen when the rock was cooler. If you have a sedimentary rock, sedimentary rocks have layering, bedding, because they are pieces that are deposited layer by layer by layer. So you look for that. You look for those smooth surfaces that indicate the pileup of those different layers. Sometimes there's fossils. So to conclude this, whenever you find a rock, the first thing you must do is look at the texture and try to figure out, is it an igneous texture, is it a sedimentary texture, or is it a metamorphic texture? So you need to figure out what the origin of the rock is based on those characteristics. And then, once you have made a decision whether it's igneous, metamorphic, or sedimentary, then you can go into the more detailed rock names of, for example, is it a basalt, or is it a rhyolite, or is it a sandstone, or is it a conglomerate, or is it a schist, or is it a gneiss? You see, then you can make a better determination of what the rock name is. But make sure you have the correct rock name that goes with the correct origin, because you don't want to pick up a rock and say, oh, it's igneous, it's a schist.